Professor Kashiwara, we want to congratulate you for being awarded the Abel Prize for 2025.
Thank you very much.
The citation from the Abel Committee reads as follows: for his fundamental contributions to algebraic analysis and representation theory, in particular the development of the theory of D-modules and the discovery of crystal graphs. You will receive the prize tomorrow by King Harald of Norway. You are the first Japanese national to win the Abel Prize, which is also noteworthy. Our first question to you are, what kindled or sparked your interest in mathematics in the first place? And when did you discover that you had a special talent for mathematics?
Yeah, I think that is not easy to answer. But I can say that anyway, I like mathematics always. And since perhaps when I was a kid also. And perhaps I was much better than usual kid, that's true. But I don't think I'm very much talented. Anyway, there are many mathematicians who are talented since he's a baby, but I'm not so, not like that. But I can say that I started mathematics because I think that is mathematics is somewhat very logical, but also logic, but also somewhat very friendly to human being. I think so. So that is what started. I like mathematics.
I see. We talked a lot about the cranes and the turtles problem.
Yeah.
Yes, and when did you solve that problem? How old were you?
No, I didn't solve it, but I think the solution is very well known, and I think yeah. So as you know that the problem is for turkeys and cranes, and crane have 2 legs and turtle have 4 legs, and they know the total number of the legs and the total number of the cranes and turtles, and what is each number of the crane and turtles. So that was the question, and of course I think that is we can solve it, but and I learned how to solve it, but it's very tricky, in fact. And I think when I learned it first time, I didn't like it at all, because it's too tricky. And so, and after that, I learned that you can solve it very easily using X and Y's, the algebra. And then you don't need a trick, you just manipulate the way. So that's a very natural way. And so that is, I think that is what the mathematics, the aim of mathematics.
Yeah.
So it means that you don't need to think much. Just if you use the X and Y or those kind of things, then you can solve it, or you can do it very naturally and very easy. Yeah. So that is, so I think somewhat that is mathematics.
Yeah, and you were fascinated by this.
Yeah. Yes.
Were there persons that influenced you in your formative years before you entered the university? Not many, but I think sometimes I learned some existence of some books, and they give some books, and for example, some teacher in mathematics give the book on geometry
projective geometry.
Projective geometry, yeah.
Projective geometry. And so I learned it, and then at the last, they said, in two-dimensional case, it's different. So at more than 3 dimensions, there's only one solution, and in 2 dimensions, it is not. And I was very puzzled, in fact.
Yeah, okay. Okay.
Yeah, but anyway, so I learned. So some teacher taught me an existence of the book, and that I can borrow the book from the library.
Yes.
And so.
Okay. Your prospective advisor at the university, Mikio Sato, said of you that you learned Bourbaki, Grothendieck, and these things when you were 18 or 19 years old. Yeah. He said you studied it by yourself with no teachers. Why were you so fascinated early on by this type of abstract mathematics?
So what happened is it's the similar things. So I was getting the course in mathematics. I think that was in algebra, algebra course, and the professor taught me the existence of EGA, elemental geometry algebraic, and Bourbaki I can remember very well. But anyway, so the EGA, and so I started to learn to read the EGA, and that is very easy to read. In fact, I think that is a well done book, and so I was very happy to see that.
Yeah. And you didn't have any problem with the French?
I had a problem, yeah. But I learned French, so when I entered the university, besides English, you have to learn another foreign language.
Okay.
And I chose French, but of course I can't read very bad in French.
Okay.
So so they give Petit Prince for the textbook of the French course, and still it was hard to read it.
I see.
It was not so difficult, but
I see.
Yeah.
I see.
Anyway.
Your advisor at the university, Professor Mikio Sato, has been described as a visionary mathematician. Your master thesis from 1970, when you were 23 years of age, where you developed Sato's idea of D modules, was described as epoch-making. Please comment on this and also on how and why you got Sato as your advisor.
Yeah, so I think Mikio Sato, Professor Sato, is in those days already he is well known at least among mathematicians, and he is somewhat a very attractive person as a mathematician. So Komatsu, another professor, the younger professor, came back from the United States, and he started to organize a seminar with Sato. And Sato started to create the so-called micro-local analysis. So micro-local analysis is to study the functions not only on the space, but the space with codirection. So on the cotangent bundle. So that was his idea. It was a very new idea, and I think, of course, there is something before, but no one thinks that is a local idea. Locally, it can happen, and so that is Sato who thought that it's possible to study micro locally. singularity functions. And he started to create the theory. And fortunately, I was there. I was participating in his seminar and started to collaborate with him. Mm-hmm. It is very lucky. And Kawai, a senior person, so he was a student also, and we started to collaborate and to construct macro analysis. And it was a very happy moment, and because of Sato, I learned many things. And I think this prize, I got Abel Prize. I think that is because Sato gave a good lesson to me.
You say that, and you said at least to New York Times, you say that Sato wanted to bring the equality world into analysis. So this is the marriage between algebra and analysis.
Yeah, we can say so. Yeah, and geometry. So as you know, in mathematics, geometry and algebra and analysis. Those three are three main divisions. But I think somewhat the module combines these three. I think that is, I'm not quite sure that, so Sato himself started to study the module because of that. But eventually that is what happened. So I was lucky to start with the theory of the modules and to apply those representation theory and those kind of things. And I think I was lucky to start study from the theory of the modules.
It was absolutely a happy circumstance. Do you so? You told us that it was an advisor at the university who suggested to you that you should read the EGA. Yeah. Was that in order to prepare you for studying with Sato?
No, not at all. I didn't think about that. Yeah, perhaps, I don't know how Sato thought, but by myself, I have no idea that those two connections. But certainly, that helps a lot. And in fact, Sato did something on the, for example, not exactly, so he developed in his way that homological algebra in his way. And I think he didn't know so of course the homological algebra existed already and developed by Grothendieck and so on. And I think he didn't know that, but I think he has some idea and he did some of them. Yeah,
but then,
independently.
But then you write your master's thesis in 1970, which contains so much fundamental stuff. For instance, you prove the Cauchy-Kovalevskaya theorem in your, which has to do with existence of local solutions. But you had your own versions of that, which of course fits in the framework you're talking about now. Could you describe it to us?
Yeah, but I think somewhat I can say that part is already included by the idea of Sato. Sato started the modules, and himself he didn't develop it, unfortunately. I think he is good to give a starting point of the theory, but I think never completed by himself, I can say. And so I started from his idea, that's true. But if once you know the idea, after that it's very easy to fill it up, because because as you know that it's like a climb the mountain. So you know the mountain, you see the mountain. So perhaps you have some route, you have to look for some route, but you can get it. So it's something.
You make it sound so simple.
So I think that's what happened. So Sato showed that there is a mountain over there. So
and you climbed on Sato.
I think until that point, influence of Sato is very big.
But the statement, as you phrase it, is if the function is non-characteristic, then the inverse function commutes with a solution functor. We're coming back to D modules more closely, but can you connect it back to the original Cauchy-Kovalevskaya theorem in any way, so that we see that there is a connection? So where are the solutions and where are the differential equations?
I think it's difficult to say. So I think one of the ideas of Sato is, so we have a real world. So there's a real manifold, and so he thinks that it is not a good point of view. A good point of view is you have a real world, but that is surrounded by a complex world. And so the real world is determined by this surrounding complex world. I think that is his main idea. And so the complex world is in fact more important than real world. And if you know the complex world, and then you can know the real world. So that was, I think, his idea and the starting point of hyperfunction theory of Sato. And so Cauchy-Kovalevskaya theorem is, I think, the main part is concerned with the complex world. And so the next idea, Sato's idea, is so now you can connect it to the real world. So that part is so I think so he succeeded with myself and Kawai to construct micro-local analysis, and that field, that part to understand how to understand real world through the complex world.
And that comes to its culmination in your paper together with exactly Sato and Kawai in 1973.
We can say,
But explain to me. So,
yes.
An important factor here is that you look. A key actor, at least, is the cotangent space, or as the physicist would say, the phase space, which is position and momentum. It plays such a prominent role in the wave front and all of this, the real and the complex world. Can you explain to me why the cotangent space should play such an important role?
So that idea, of course, existed since a long time. I mean, for example, Fourier analysis. So that is we can say that is some kind of incarnation of those the cotangent boundary was symplectic geometry, and in physics it also. So the moment, as you said, the momentum space. So, but I think. That what is important there was so that existence was known global in a global sense, but locally, I think the relation was not the existence is not how to say. They don't think such. I mean, the cotangent boundary is important in a local sense. So that
because you have the code.
That part is important and very new. So that part is
Yeah. Could I just interject with something? We are talking about your master thesis when you were 23 years of age, and you wrote it by hand, I gather, in Japanese, and it took 25 years before it was translated into English, which is remarkable.
If I looked at now, there is some beginning of the theory I can see, but that's right, yeah.
But how, so these ideas became influential, and given that they were only in handwritten Japanese, somehow the ideas must have come out. Was that through the 73 paper with Kawai and Sato? Or?
Yeah, but in my master thesis, micro-local point of view there is, but very small. So that is developed after. So that is micro-local. So my master thesis is written, I think, 71 or something. And after that, I worked with Sato and Kawai, and continued 5 years or something like that. And so the micro-local point of view is fully developed after.
So in that same paper from 73, you established the involutivity of characteristics of micro-differential systems, which of course had been touched upon by Gilman, Quillen and Sternberg in 1970 and proved totally algebraically by Gaber in 81.
That's right.
But what is the involutivity of characteristic of micro-differential systems?
Yeah, that part is very important because you see that so it concerns on the cotangent bundle. So on the cotangent bundle, so you have some subspace inside, but the important part is not the arbitrary subset appears, just involutive one, so a good one with respect to symplectic geometry appears. So that part is, I think, important, and
it has to do.
Those Jimmy Sternberg or what? I can't remember.
But that has. So another word for this is integrability, isn't it?
Yeah.
Yeah, exactly. So and also in 73, it must have been a very good year. You have your first index theorem, which I understand it has a special place in your heart, and you revisit it in 2030 together with Shapira, with the micro-local Euler characteristic and Hochschild homology. So why does that hold a special place in your heart?
That's better to go back a little bit. So at my master thesis, I proved the index theorem for one-dimensional case. And for higher dimensional case, I didn't know how to do that. And I think that was somewhat my concern in those days. And so I can remember the original index theorem and how I did it. I know the afterwards, but so that was a somewhat very surprising fact. In fact, in a foreign sense, because the index theorem usually so that is somewhat a little bit global theorem. So you have to know the local information at every point. But my index theorem is not like that. So it is enough to know some rough part or some generic part. Only generic part is enough. So that is somewhat. I'm very surprised when I proved it. Yeah. Of course, somewhat it can be expected because so that involutivity. So involutivity means So the set in those kind of things in the simple geometry, so no arbitrary subset doesn't appear, but only the invertible one that does appear. And so there's no small subset which is invertible. So it means that the generic part determines the whole thing. So that can be expected, but perhaps I don't know. I can't remember anymore. But I mean, perhaps when I look back afterwards, then perhaps we can expect. But
both suspected and surprising.
Yeah, I think that is, you can say afterwards, but
not in hindsight. So, okay, so one of the things that really fascinates me about what you've been doing, of course, is in 1980 you do the Riemann-Hilbert correspondence, which in your world is an equivalence between the derived categories of certain D modules and constructible sheaves. And the algebraic case had been done 10 years before by Deligne, and Mebkut, I think, did something very similar at the same time as you were doing it, and Beilinson and Bernstein were also in the neighborhood. But do I understand correctly that the hard part here is understanding how to restrict so that your functor becomes fully faithful? Is that the key problem? You have this solution functor?
Yeah, there are many ways, but I think the most difficult part was the correspondence between two things. So topological part and the algebraic part. Algebraic part corresponds to D modules, and topological part corresponds to monodromy. And algebraic part, it is not only on D module, but so-called regular type D module. But that is somewhat very hard, very difficult concept, in fact. Regularity is somewhat not easy to handle. And so Beilinson, Bernstein did something, but anyway, that part is hard. And in fact, it took a long time for me to define properly the regular holonomic D module.
So actually, you said monodromy on the constructible sheaf side. Perhaps it's good to go back to Hilbert's 21st problem and connect. So which part in Hilbert's 21st problem corresponds to D module, and which one corresponds to the constructible sheaves? And what is Hilbert's 21st?
So the original problem is that monodromy, so-called the monodromy. So the solution to the linear ordinary differential equation is not univalent. So that has a multivalent, and if you go around the singularity, then it is not unique. But so if you go around, then so-called the monodromy appears. And so the original problem is the monodromy and the linear ordinary differential operators with regular singularities correspond. So that was the original one.
So the D modules correspond to the differential equation, and the monodromy to
correspond to the
constructible sheaves.
Exactly.
And it has been called parallel or a generalization of the equivalence between the de Rham cohomology and a Betti or singular cohomology. Is that a valid point of view?
No. I don't think so. I don't. It's a little bit different point of view. That part is very different.
But the Durham sheaf figures prominently.
Yeah, but the concerns are different, I think. Yeah, that's a long history. So.
But it's an important result. So.
Yeah, of course. But I think it's not exactly the same category. Yeah. In the sense that for example, drum cohomology and bed cohomology, or I don't know how to call it, that topological one. So they concern the difference between them. But D modules and monodromies are so different. So the correspondence itself is important. And but for the other one, bed cohomology and drum cohomology, so there is something. So now Grothendieck wanted to unify it in the languages of motif. So there is something motif, and one aspect is bed cohomology, and the other aspect is drum cohomology. So one thing, and you can see it this way or another way. You can see two kinds of things, or another kind. There are many ways, and but I think it's a little bit
different. But it has to do with the differentials, which are very Durami, and the topology or the geometry on the constructible sheaves of solutions and monodromy. So somewhat it's what you are saying is right, but it's not. Of course, nowadays they are mixed. Some part is mixed. Yeah, for example, the work of Morihiko Saito or Mochizuki, Takuro Mochizuki. So those they connect to things, but then you need more information. Yeah. So let's see. So D module. So that is dx. If x is your manifold, that is the algebra of differential operators.
Yes.
And so that explains the D modules, which then control the differential equations.
Yeah.
But how do constructible sheaves at all look like monodromy?
So that is exactly the same. But constructive or monodromy is so locally the structure is simple, and so globally how they are connected globally. So that is a monodromy. And sheaf, so that is exactly the word to describe global and that connect global and local. So I think nowadays they understand monodromy and constructive sheaves or sheaves is almost similar thing.
You patch together so that you actually have the loop around.
Yeah.
So later on with Enolo in 2011, you actually were able to remove the regularity condition at the price of replacing the sheaves with in sheaves.
In sheaves,
So regularity, then you remove that assumption, and then you introduce that you have, filtration, in systems. So why does the in system help you resolve the singularity, if I may?
So what happened is, so it concerns not only the regular holonomic, but irregular case also. And in regular case, the behavior of the solution at a single point is rather easy to understand. But in irregular case, that is more complicated. And takes a long time to understand how to control the singularity of functions to the singularity when irregular case, and so after that we know that so that is a rather tricky part. Tricky part. So it takes 20 years to reach that solution.
And you had inspiration from Shapira and Tamarkin on these end questions, or was that later?
Yeah, it related. So it related, but I think that's a rather tricky part. So what happened is how to say. So the main idea is to add one variable, but that one variable is rather. What is that one variable? That is not easy. I don't understand very well. Of course, there can be a better understanding, but yeah.
But very surprising to you that you actually replacing sheaves with end sheaves is not such a dramatic thing, but it seems to me very dramatic to remove the regularity condition. Was that surprising to you that such a slight extension here actually would resolve or allow you to take away the regularity?
Yeah, but it's a long history because with Shapira, I did. In the beginning, we did it. To control the singularity of functions. So that is a starting point of sheaves. But so gradually it is developed, and finally we reached that solution. But I think that history is rather long, and
exactly.
I can't explain very well.
But on the other hand, so the Riemann-Hilbert correspondence and D modules, they figure prominently in the geometric Langlands conjecture, mostly recently in the proposed proof by Gatesbury and his collaborators. What are your thoughts on this? So it sits so centrally in there. I think for those, for example, for geometric Langlands world, of course, D modules, you need D modules anyway. But so it's something like the tool that you can admit. So I mean, it's like the x and y in the algebra to describe that algebraic equation. And nowadays, those are to manipulate x and y. So that is a basic idea. You forget about that. Anyway, that is a very basic tool. And so it's like that. And of course, to solve the geometric Langlands and so on, so it's not enough. You need extra idea. Oh, sure.
Yeah, x and y is not enough at all. So, something like that.
But I should mention that UNO has proven several conjectures, or at least addressed several conjectures of Hernandez and Frenkel on Langlands duality since. So let's see. So as I was just reminded, I have to hurry here. You mentioned that for a time you didn't have direct application of your theory of D modules, but that Brzezinski came to you and suggested in 1979, I think it was in Paris, or wrote a letter, and suggested that the Kasdan-Lustig conjecture should be something that should be approachable through your means. So how did that start?
This fits into what is also remarkable about your publications, is that you have authored more than 250 papers with 70 co-authors, an unusually large number for a mathematician.
Yeah,
but would you comment on this, and in part on your cooperation with Jean-Luc Brylinski in 1979, which led to a proof of the Kashtan-Rushdie conjecture?
Yeah, that's right. Yeah.
Could you comment on this?
Yeah, but I think I can comment first.
Yes.
70 is rather exaggerating. I think 50.
50. Okay, I'm sorry about.
Yeah.
All right.
Yeah,
okay.
70 is perhaps so that is comes from the Masai net.
Yeah, that's right.
But Masai net, it includes the if I write the paper in some book,
okay.
and then there's other contribution, and they thought that.
Okay, but 50 still. Yeah, all right.
But 50. Anyway, so Jean-Luc Brylinski's case. I knew a little bit about, but I was not a specialist in those representations here. And so it was Jean-Luc who came to me, who wanted to see me, and we discussed at a cafe at Jussieu in Paris. And that is, so he explained the Kashtan-Rushdie program, and perhaps we can solve it by using the D modules. And of course, there is we need something else, and so we started.
And this was very successful cooperation.
Yeah, it was successful. But there is one point where we need something else. Yeah. Okay. Yeah. And so the same time, Beilinson and Bernstein.
Okay.
So perhaps I should go to crystal bases. So later, around 1990, Rushdie, the name appears again, where you prove that his canonical basis for representations of quantum groups on a vector space on the field of rational functions in Q over the rationals crystallizes, as you call it, as the temperature goes to zero. That results in a combinatorial description by means of what you call a crystal graph. Can you tell us briefly about that while I fix my...
So perhaps I think it starts from the... So Sato, I worked with Sato and on microlocal analysis. And then Sato moved the subject, changed the subject, and he started to study exactly solvable model, so-called exact solvable model in mathematical physics, or and so there. So he worked with Miwa and Jimbo, and Jimbo introduced the so-called quantum group, and that is independent with Drinfeld. And so of course, I knew them very well. That they are, I collaborated with them sometimes, and so I knew very well. And so that concerns with some parameter Q, which correspond to the temperature. So I knew that it plays an important role, and I wanted to study what I already studied about that. But so in the beginning, I thought that at Q equals 0, so at least in the case of exactly solvable model, so what happened is at q equals 0, that is the phenomenon. It's very simple, and the problem is at the critical point. And the critical point and q equals 0 transforms by some kind of inversion formula. So that is what happening. And so anyway, I thought at q equals 0, there is something good happens. But I spent a long time, not a long time, but had several months to what is it. And finally, I thought anyway. So if you consider the representation itself, then there is something good happens.
Yeah. You must have been very proud.
Yeah. So that is a crystal base. And so then what happened is, so like the things is, or the material is moving, but at the temperature is 0, so it's crystallized. So there is some concrete base appears. Yeah. So that was
and that is totally combinatorial. The base.
Yeah, and then we can analyze it combinatorially. So that is a main.
Yeah, and you got some graphs also.
Yeah.
So
yeah. Then combinatorially, so it means so by a combinatorial method we can describe the representation itself, and then the representation itself is rather difficult to analyze, but combinatorially it's not very difficult. So that is what.
So how does this propagate from the Q is equal to 0, the temperature being equal to 0?
Yeah.
Does that lift onto bases with positive temperature?
Yeah.
So you actually get a whole.
So that is it afterwards. So in my case, I started at Q equals 0, and at Q equals 0 there is a good basis. And after that, we can extend it to
exactly.
case.
So you've returned to this several times. So for instance, in 2018, together with Kang and Kim, you discover a Schur-Weyl duality relating quantum affine algebras to certain Quiver-Hecke algebras. So that is fairly recent. So do you foresee that you will continue working on this?
Yes.
Yeah, this is something that you.
Yeah. That's right. Yeah, that part is still I'm working on that.
So is this the main thing you're working on, or are there other ideas that you?
Yeah. So I'm working on that, and together with so-called cluster algebra. So
exactly.
Cluster algebra is introduced by Zelevinsky and forming Zelevinsky, and unfortunately Zelevinsky passed away.
Yeah.
So that is what I'm explaining in our lecture.
Oh, brilliant! We're looking forward to that.
Yeah, not exactly, but yeah. So that part is now what I'm interested with, and I'm working.
I know it's completely fair, but if I should challenge you, which of your mathematical achievements are you most proud of?
Yeah, I think it Riemann-Hilbert problem. Yeah, okay. And crystal basis. Yeah.
Crystal basis also.
Crystal basis. Yeah, for two things.
Okay. Another question: working in isolation or working in collaboration, what do you prefer?
I think collaborate is. Yeah, I think it's different when I was young and nowadays.
Okay.
I think so. Yeah. Nowadays I need some. Yeah. I was I'm now working with some mathematician younger generation. Then I can get some energy from them, and that is important.
Okay.
But when I was young, it was not like that. So, so the meaning of collaboration are different now.
I see. It's a question, interesting question that was raised by Lennart Carlsson, who won the Abel Prize early. And this goes as follows. Where from and how do ideas arise, is the question. Presumptions are the enemies of discovery. If you sort of fixed on something without any other thoughts.
Yeah.
But Carlsson also said the following: the most important aspect in solving a mathematical problem is the conviction of what is the true result.
Yes.
Do you agree with that, or?
I think both are true.
Both are true. Both are true.
That's. Personally, I can give you some example. Yeah. So as I told, I was working with Sato on micro-local analysis, and after that, with Pierre Shapira, I worked on the micro-local aspect of shift theory. And what happened is, when I was working with Sato, I thought that micro-local analysis can be only applied to the singularity of functions. I think that is pretty assumption.
Yes.
And so that is what do you call
presumption? No.
Yeah, presumption, and that was not good.
Yes.
So that stifled your imagination.
Yeah. After that, I worked with Shapira to find we can apply for other things, and if we forget presumption.
Okay, very good.
So,
I see. Yeah. What about this old question that always pops up? Pure versus applied mathematics. Should we distinguish?
Yeah, I think that's a good question. Yeah, I think perhaps not, but I think the problem is we cannot work both. I think. I think so. Pure mathematics can be applied to applied mathematics.
Yes, absolutely.
Absolutely. Yes, but if you want the pure mathematics, then I think if you perhaps it depends on people. But for myself, for example, I cannot do the two things together. I mean, to consider the applied math and to consider pure math. And so, but I think it's important to consider both. I think, but I think for usual mathematician like me, cannot
distinguish.
Study both at once.
Yeah, I see. Okay, Bjørn. Sure.
Well, there are so many more. I really wanted to press you more on your mathematics and get your ideas out of this, but I guess we have to close pretty soon now. And thank you for sharing these thoughts. But before we close, we generally often ask, do you have any special interests beside mathematics?
Besides mathematics?
Is there a life beyond mathematics?
Not many, but of course, I like some of the music, yeah.
You like music, yeah? What sort of music do you enjoy?
Nowadays, I like very much Indian music.
Indian music.
Yeah,
Yeah, you learned to play this. You learned to play rather recently, didn't you? Did you learn to play the sitar or something like that?
No.
No, that was wrong.
No. I just to listen. And so there are basically two types of Indian music: Carnatic and Hindustani. Hindustani is more north and Carnatic is south.
Exactly.
And sitar is the Hindustani. And I like it. Carnatic. And Carnatic doesn't use sitar.
Exactly.
Yeah.
Okay, so that is one, and you are staying with Indian music. You are not moving around to different places. It's Indian.
Yeah, no. I started to like Indian music when I was in Chennai.
Exactly.
Yeah. So in Chennai, and so there is a music season, music month. So that is in December. So in December there is a music.
It's a festival or something?
Yeah, festival. Well, 1 month. 1 month.
And you were there during that?
Yeah. So I went every night, every evening to the theater with mosquitoes.
But there is also a rumor that you do play table tennis.
Yeah.
I don't know. Do you play table tennis now, or is there?
No, not anymore, because I broke my knee. So
is that long?
Because of that. Wow.
But you were playing actively table tennis for a while, didn't you?
Yeah, for a while.
Yeah, exactly.
You played in competitions also?
No, but I played with Jean-Pierre Serre. And
with Jean-Pierre Serre?
Jean-Pierre Serre. Jean-Pierre Serre is good also. And I was beaten by him.
Yeah, okay, so this is a question. You need to be very quick in table tennis. But you're quick also with mathematics and table tennis.
No, I'm not so good in table tennis. Yeah, at least Jean-Pierre Serre is much better than me.
I would be totally happy with being beaten by Jean-Pierre Serre in almost anything, so that's perfectly fine. So on behalf of the Norwegian Mathematical Society, the European Mathematical Society, and both of us, we'd like to thank you for this very interesting interview.
Yeah.
Thank you.
Thank you very much.
Thank you very much for that. Yeah.